Hi students, we are going to go through answers for these questions. I'm using a different software, so hopefully you'll be able to read this. So I'm going to go through, do some explanation, get answers there. So the first question is, if possible, name a number that is both rational and irrational. And, well, let's try this. This is not going well. This is not possible. Okay, and the reason it's not possible is real numbers are all the numbers that we use. There is such a thing as imaginary numbers, but we're not really worried about that. And real numbers break down into two categories, and the categories are rational and irrational. Underneath rational, you have some other types of numbers. You've got whole numbers, counting numbers, or natural numbers, and integers. Under irrational, nothing. So you can think of these as being in two separate boxes. Okay, so that's not possible. All right, a number that is an integer but not a whole number. All right, well, I think I'll approach this one by doing, all right, integers are whole numbers and their opposites. So like -3, -2, -1, 0, 1, 2, 3, and so on. Whole numbers just start at 0. So these are whole numbers. So if I want to name a number that is an integer but not a whole number, I need to name one of the negatives. So I'll give my answer. I'll say -4. Any negative number would work. All right, next is, if possible, name a number that is a rational number but not an integer. All right, so a rational number is what you get when you divide two integers. And sometimes when you divide two integers, let's say 5 divided by 1, you get an integer. Or let's say we do -12 divided by 3, right? We get -4, an integer. Sometimes when you divide two integers, you do not get an integer back. So for example, if I do 2 divided by 3, well, that is 2/3. You can think of it that way, or 0.6 repeating. Right? So a number that is a rational number but not an integer, I'm going to go with 2/3, which is the same thing as 0.6. All right, is square root of 5 equal to 2.24? No, because the square root of 5 is an irrational number. So that means the decimal places keep going and going. Never ends, never repeats, such that you can spot a pattern in there. So this is actually 2.236, blah, 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 blah. So you can't ever write it exactly as a decimal because you just can't list them all because it's infinite. All right, next one is a set of odd whole numbers closed under multiplication. All right, set of odd whole numbers. I'm going to start, make sure I know my set. All right, those are my odd whole numbers, okay? And I want to know if my set is closed under multiplication. So the way I check is I pick two odd numbers, I multiply them. So I picked 9 and 3, and I get 27. And then I ask myself, hey, is 27 in this list? And yeah, it's not written, but it's part of the ... So based on using these two numbers, it seems to be closed, because closed means the answer you get belongs in the original list of numbers. So I'm going to do something like, how about 11 times 7? That's 77. 15 times 15, 225. And, I feel pretty convinced that this is closed. if I multiply two odd numbers, I will always get an odd number back. So my final answer is that it's closed. All right, now I've got convert this number, and I hope I can figure out a place to have some room here. 2356 to base 10. And I'm going to write this up here. Okay, so I'm doing this problem up here. All right, so when I convert to base 10, I need to say, all right, this guy's in base 6, so what are the place values? And these are the ones, all right? So this is 6 times 1. These are the 6s. So this is 5 times 6. This place, I go 1s, 6s, 36s. So it's 3 times 36. I'm regretting making this so big because I don't have my calculator with me. Next spot over is 2 times, and this spot is, I've got 1s, 6s, 36s, and that's 216. All right, so now I need to add these all up. So I'm going to add 6 plus 30 plus, don't fail me now, 108 plus 432. All right, so if I add these all up, let's see if I can manage this in my head. Let's see, 432 plus 108 is going to be 540. Plus 30 more is 570. So 576 is the answer. All right, next page. All right, now I'm looking at converting 324 to base 3. So this is in base 10, our normal numbers, and I'm going to base 3. So I need to think about what are my place values in base 3. And these are my 1s, and these are my 3s, and these are my 9s. So I'm multiplying by 3 each time here. So 1s, 3s, 9s, 27s. What was I thinking making this so big? 81s, 243s. So I just kept multiplying by 3. The next one is going to be, I don't know, times 3. It's going to be in the 700s, 729. 729 is much bigger than 324, so I don't need that. All right, so now I'm going to come back here and I'm going to say, how many groups of 243 can I get from 324? That's going to be 1. So now I come over here and I take 324 and I subtract the 243 that I've already used. And that's going to be a 12, so that's 8, and that's gone. All right, I've got, wow, this is interesting. So I've got exactly 81 left. So I put my 81 there. I had no idea it came out like this. I subtract the 81 off of here, and I'm out already. So what I have to remember to do is say, hey, I don't have any 27s, any 9s, any 3s, or any 1s. Okay, so my final answer is 1, 1, 0, 0, 0, 0, base 3. Okay. All right, next one. Find the number that comes before 400 base 6. So I like to do these using base pieces. So this number is represented. Remember, I go babies, longs, flats. So I've got 4 flats. I've got 0 longs. I've got 0 ones. So when I find the number that comes before, I want to take away a baby. Take away 1. Right? have no babies to take away, and the way I can get those is to break. Okay, so I can take this flat, and I have to think about the fact, hey, I am in base 6. So it takes 6 babies to make a long, and it takes 6 longs to take a flat. So when I break this guy up, I get 6 longs. All right, so now that's been used up. It's split into another representation. I still have no babies to take one away, so I got to repeat this process. I got to take this long and make that into 6 babies. So now I can finally take one away. I got rid of that, and now I record what I have left. I have 3 flats, I have 5 longs, and I have 5 babies, and that is base 6. All right, so I've got this fraction here, 6 over 70. I want to know if it terminates or repeats, and I have to use the method shown in class. So I take the 70 and I make a factor tree. So that's 7 times 10, and that's 5 times 2. So this is 6 over 7 times 5 times 2. This 7 right here tells me it repeats. To terminate, the only numbers that can show up in the denominator are 5s and 2s. All right, so this one has a 7 thrown in there. Anything other than just a 2 or a 5, any other digit or any other number is going to make it repeat. So this repeats. This one is 3 over 80. Right, so I do the same thing. 80 is 8 times 10. That's 5 times 2. That's 4 times 2. That's 2 times 2. So we've got 3 over 2 times 2 times 2 times 2 times 5. So I look at the denominator, all I see are 2s and 5s, terminates. All right, next page. All right, here's some set operations. So remember, we're going to do what's in parentheses first. This is what I do first. It's in parentheses. It is an intersection. So when I do B intersect C, I am going to look at B and C, and I'm going to only list the numbers that are in both sets. So to be in the intersection, you have to show up in both places. So that's 2, 3, and 6. So that's not my final answer because I've only done half of it. Now I have to take the union of A, 1, 2, 3, 4, and 5, and my intersection 2, 3, and 6. Union, just start with the first set, and then if there's anything in the second set that you haven't already written down, write that down. Because union just combines the 2 sets together, literally just dumps them into a pile. If there's duplicates, though, you don't keep duplicates. Okay. All right, so that's the first one. Second one, I'm going to do a union, and then I'm going to intersect that. So I'm going to do A union B. So that's 1, 2, 3, 4, 5, because I'm just listing A. Now I'm going to come back in B, and I'm going to say, hey, am I missing anything? Yep. Okay, that happened. So 6 and 8. All right. Now I'm going to do A union C. So 1, 2, 3, 4, 5. And then I'm going to add on 2, 3, 4. I need 6 and 7. Okay. So now I intersect those. So I look at this set. I look at this set. And I say, hey, which numbers show up in both? That's 1, 2, 3, 4, 5, and 6. 7 and 8 don't make it in because they don't show up in both places. Okay. Next one, I've got a bunch of operations here. I meant to put this on here. This should be, well, you saw this in the videos. Sometimes they use that little hash mark or whatever to be the complement of a set. All right, I'm going to keep going here. So I am going to need to do what's in parentheses first. And I'm going to need to do the complement of C before I do the union. So I am going to start by creating the complement of C. And the way I do that is, remember, complement of C is anything in the universe that is not in C. So I like to list the universe. Messy, I see. And then I go through and I cross out the ones that are in C. And what I have left are the ones not in C. So I cross out 2, 3, 4, 6, and 7. So the complement of C is 1, 5, 8, and 9. Okay. Now I have to do A unioned with this new set right here. So I list A. So 1, 2, 3, 4, 5 is what's in A. And then I add on anything from this set that's not already there. So that's going to be the 8 and the 9. Okay. Final operation is intersection. So now I am going to intersect this set right here with A. So I get 1, 2, 3, 4, 5. And that's my final answer for part C. Okay? All right, draw a Venn diagram to represent A union B minus C. So this is going to be a Venn diagram with 3 circles because I've got 3 sets, A, B, and C. So this one will be A, this guy down here is B, and this guy's C. Okay, so I'm going to start left to right. I'm going to do the A union B. So A union B means combine A and B. So that means I'll start with A, and I'm shading in all of A, all right? And then I add on anything from B that's not already there. So some of it's already there. I add on the rest of it. Okay. All right, so that's A union B. Now I am supposed to remove C. So what I have to do is remove those 2 parts that are shaded and overlapping with C. Let's see if I can pull this off with the eraser. So that's going to be, all right, that did not go well. All right, I'm going to try this again. I'm going to draw this. Wow. All right. All right, A, B, C. All right, so A union B, right, is both of those circles like I had, but you can't see anymore. And then I'm going to remove C. So that means anything in the C circle actually is not shaded. So this will be my final answer. So I was trying to be really slick there and start with it all shaded and then just erase these parts. That didn't go well. All right. All right, so this is A, B, C. A intersect B intersect C. right, is if I'm intersecting all of those, I'm looking for the area that is in all three circles. So it's what's in common with all three. And that's the bullseye right here. Okay. Now, I haven't done the complement yet. So now, this is not my final answer. This is just to help see the final answer. When I do the complement, I'm doing everything in the universe that is not shaded. So that means I do the negative, like if you think of the negative when you're talking about film. Anything that was shaded becomes unshaded. Anything that was unshaded becomes shaded. Right? So the only thing left unshaded is that bullseye in the center. All right. And that looks like it's it. So that's it. Please make sure you email me if you've got any questions. Thanks.